I want to start this section off looking at an example. Let's look at the function. So we are working with multivariable functions at this point in this chapter. So we're going to look at a function of two variables that's equal to x squared minus y squared over x squared plus y squared. We can immediately see that the domain of this function is everything except for 0, 0. Because at 0, 0, the bottom of this function equals 0. And so things will break. But we want to know, how does this function behave around the origin? So let's graph it. We'll go ahead and put an x squared minus y squared. Divide that by x squared plus y squared. And we get this surface here. If we look at it, it looks kind of like a plane that someone pinched at the origin. And if we look at it from above, it kind of looks like it should do this. It should go to 1. It looks like that's approximately where things are going. Except if we look at the bottom, it looks like things are going to -1. So what's really going on there? Basically, what we're doing is we're trying to find a limit. We're asking, what is the limit of this function as we go to the origin? And we can denote that idea using our normal limit notation, except here we are saying as both x and y go to 0, 0. We're asking, well, first of all, does this limit exist? And if it does exist, what is it equal to? Now, in this particular case, the limit doesn't exist. And we can show that by examining two different ways to approach the origin. If we, say, assume that we approach along the x-axis, there we have that y equals 0, and so our function, f of x 0, go ahead and replace the y's with zeros, get x squared over x squared, or just, we always get 1, assuming that x is not 0 as well. For any point except for 0, if we put in for x, we always get 1. And so that means the limit of this function as we go along the x-axis is going to have to be 1 as well. If we go along the y-axis, in that case, x is equal to 0. And if we plug in 0 for x, well, now we have zeros here, but we still have a minus y squared on top and a y squared on the bottom. For y's that are not equal to 0, this simplifies to be a -1. So if we're approaching along the y-axis, this function is always staying at -1. So if our function were to have a limit at 0, 0, we'd expect these two limits to be the same. We would expect the limit to be the same regardless of what direction we approach from. So let's actually write down a formal definition of a limit of a function of two variables. So this looks fairly complicated, but we're just saying that this particular expression, the limit as y goes to ab of our function equals L, if we have this epsilon delta condition. For epsilon greater than 0, there's a delta greater than 0, so that if we're, well, first of all, we have to be in the domain of the function. That's what the D here represents. But we definitely want to be close enough that we are dealing with stuff in the domain of the function. This expression here is saying that the distance between the point xy and the point AB is less than delta, but we don't want to necessarily be dealing with the point AB itself, so we're going to say the distance is greater than 0. Then we have that the values of f of xy are within epsilon of L. So this is really just saying as xy gets close to AB, then f of xy is close to L. We're not really going to stress the actual formal definition here. epsilon delta stuff is actually very important when you get into actual proofs. It's not so much important when you're doing the computations in this course. And you probably won't see too much of epsilon deltas unless you go deeper into mathematics. Now, in the vast majority of cases that we will see in this class, limits actually are relatively easy because we like to work with continuous functions. A continuous function, or a function, is continuous at a point if we can find the limit at that point by just plugging in the point. So the limit of our function at AB is just the value of the function at AB. And we can say a function itself is continuous on all of its domain or on all of a set if it's continuous at every given point. And this includes most of the functions we want to look at, or at least it includes on most of the parts of the functions that we want to look at. So various continuous functions we have. Are, we can say, polynomials. So kind of an example of this, we can say f of xy is x plus y squared. We could have more complicated terms like 5x cubed y to the fifth, something like that. That's a polynomial. It just involves products and sums of powers of x and y, or x, y, and z if we are actually dealing with a function of 3 variables. We can look at rational functions. A rational function would be something that is a polynomial divided by a polynomial. So you could say x squared plus y squared over 3x minus y cubed. Now, this is what I've written here is not continuous for every point x and y. This will not actually be continuous at any point where y cubed equals 3x, say. But they are continuous on their domain. At any point in their domain, a rational function will be continuous. So as long as the bottom here doesn't equal 0, we're fine. And in general, anything that is kind of built up out of trig, logarithms, exponential functions, even square roots. But square roots we have to be cautious about where we're plugging 0 into the square root, because that will be on the edge of the domain. We generally want to have a point that's inside of the domain. So we'll kind of ignore the points along the edge. But generally, as long as we don't run into cases where, say, we have 0 in the denominator, we have a negative in the square root, or 0 or a negative inside a logarithm, things like that, as long as we're not dealing with stuff like that, we're generally fine. And we can just find the limits by plugging in the value. And so really that just gives us our idea that we generally use in Calc 1. If we want to find the limit, just first things first, try to plug in the point, and that's usually going to be your answer, unless you have some weird function. But what if we're working with a function that is not obviously continuous, or working with a function at a point where it's not obviously continuous? Well, like we looked at limits of functions of one variable, there we would break them up into one-side limits, or at least that's one thing that we could do. Basically, for our limit to exist, we need to have a limit for both ways that we approach the number. And those limits had to be the same thing. This is true for limits of multivariable functions. Just like we saw here, we were able to show that the limit doesn't exist because if we approach it in two different ways, we get different results. Now, of course, here, these were not just left and right. These were actually in an x and y direction. So the different ways that we can approach our point is much larger. We have a lot of different ways to approach the origin in the plane, rather than just approaching 0 on the line. And so that's going to make showing that the limit of a multivariable function exists a lot trickier than it would otherwise be. So let's look at some various examples and see how bad it can get, to put it in a way. Let's start with the function f of xy is equal to xy over x squared plus y squared. Now, of course, the domain of this function, this is a rational function, its domain is everything except for the origin, and so it's going to be continuous at every point except for the origin. But we're concerned about what is the limit as xy goes to 0, or 0, 0, I should say. Does this exist? Does it not exist? Who knows? Well, we can go ahead and try to approach it. Let's try what we did on the first example. We'll try approaching along the x-axis. Well, there, y is equal to 0. And so our function, if we go ahead and plug in 0 for y, well, here, well, the top becomes 0, our bottom becomes x squared, and as long as x is not 0, this is always equal to 0. That's really handy. What about along the y-axis? There, x equals 0. We do exactly the same thing that we did with putting 0 in for x. We still get 0 on top, we get y squared on bottom, and we get 0. Okay, that looks promising. We got 0 in both cases. But it turns out just looking at the approach along the axes, or along directions that are parallel to the axes, is not enough. If we look at a different line through the origin, we're going to look at the line y equals x. So I'm essentially just going to take my y values here and I'm going to replace them with x's. Basically, we're looking at what happens if the values that we put into our function are the same too. In that case, we have x times x, and we're dividing by x squared plus x squared. But the top is now x squared, the bottom is just 2 copies of x squared. We can cancel the x squares because we're assuming here that we're not working at the origin. We are working with x not 0. And so if we cancel those out, we get 1/2. So along the line y equals x, we get 1/2. Probably not what you expected, but if we graph this thing, we can kind of see why that's the case. So here we're going to go ahead and put in our function of, what was it, xy over x squared plus y squared. Let's zoom in a little bit to make it a little more obvious what's going on here. It looks very similar to the last one. It looks like our plane is pinched again. But this time it's pinched not along one of the axes, it's pinched in a 45-degree angle. So along the axes, it stays equal to 0 the entire way. But if we come in along the line y equals x, which is this one here, it actually stays at 1/2 the entire time. So you can kind of tell that we've essentially taken our original example and turned it a little bit. But the point is that we wouldn't be able to tell that unless we'd already graphed it. So if we're just told to find the limit, we may not know that's what we want to do. Let me test standard there. So let's look at another example. Let's say f of xy, still going to be using a rational function here. Those generally are nice to use. But we're going to look at x squared y over x to the 4th plus y squared. Again, 0, 0 is going to be the only point that's a problem here. And we're going to want to find what is the limit as we go to the origin. does this have a limit? We could go ahead and try looking at the axes. Do we approach a particular value along the axes? We could try other lines. In fact, let's look at every possible line through the origin. If we pick the line y equals mx, so this is the general format for a line through the origin, aside from the y-axis itself. If we go ahead and do that, basically just replace the y with mx. So we have f of x, mx. We have x squared, but then we have mx replacing the y. We have x to the fourth, and we have mx squared. We can actually divide the top and bottom by an x squared. So the top will just become an mx. The bottom, the x squared, will become an x squared. And then the x squared that we have here is canceled out, and we're left with an m squared. Now what happens to this thing as we let x go to 0? The limit as x goes to 0 of mx over x squared plus m squared. Well, the bottom is going to m squared, the top is going to 0. And as long as we're not dealing with an m that's already 0, this is always equal to 0. In the case when m does equal 0, well, our function was 0 to begin with, because we had 0 on the top, we had 0x over x squared. And so we were just dealing with the 0 function to begin with. So we get 0 there as well. What about the y-axis? Because that's not actually included here, because the y-axis has no slope, or you could say infinite slope. Well, in that case, remember, that's when x equals 0. So if we go ahead and put x equals 0 in there, well, now we have 0 on top, and we have y squared on bottom. We just have the 0 function again. So it turns out, no matter what we're doing, as long as we approach along the line, we get 0. So it seems like no matter how we approach the origin, the limit is 0. So is that the limit of our function? No, it's not. The limit of this function is not 0. In fact, this function still has no limit, because we can approach the origin along curves that are not lines. Let's approach along the parabola y equals x squared. If we approach along that, we're just going to replace the y's with x squareds. So we're looking at the function of x squared. We still have x squared, but then we're replacing the y with another x squared. We have x to the fourth, then we have plus x squared squared. So on top we have x squared, on the top we have x to the fourth. On the bottom we have x to the fourth and another copy of x to the fourth. So we have 2x to the fourths. And we get 1/2. So if we approach along the parabola, we get 1/2 instead of 0. But if we approach along any line, we get 0. So this does not have a limit. Let's go ahead and graph this one too. So we have x squared y divided by x to the fourth plus y squared. If we plot that thing, let's zoom in on the origin so we can see what's going on. So it's definitely crinkled like the last ones, or pinched like the last ones, but in a weirder fashion. You can kind of tell why the parabolas are unique, because it is kind of weird. It does, the top here follows the parabola y equals x squared. The bottom, stop moving on this one. The bottom here actually follows the parabola y equals negative x squared. And you can kind of see why it's approaching 1/2 here, and it'll actually approach negative 1/2 here. It might be a little harder to see why, if you approach along any line, you do get 0. But we actually did show that. We proved that by actually deriving those limits. So the point here is that we have to be very careful when we try to find limits of functions of more than one variable. They might not turn out to be how you expect them to be, and they may be a lot more complicated than you might expect. I want to do one more example of a limit. I'm going to look at the function f of xy is xy over the square root of x squared plus y squared. This is actually problem 13 on page 950. Again, this does have a hole in its domain at 0, 0. So we're just looking at the limit. Of this function and asking whether or not it exists. This time let's go ahead and graph it right away so you might have a better idea of what it looks like to begin with. So we're going to graph xy over the square root of x squared plus y squared. And we get this surface here. Now this time, you could kind of describe it as pinched a little bit, but this time it doesn't look like there's going to be a problem. It looks like everything's going to 0 at 0, 0. We definitely have the point 0, 0, 0 right in the middle there. And so we expect, once we look at the graph, we expect that we will have a limit. But that's not a proof. We have to actually go ahead and prove that. So we're asking, is this equal to 0? Now, how would we prove this? We don't want to look at all the different lines and parabolas that go through the origin, because that wouldn't be enough to prove it anyways. We'd also have to look at other curves like cubics, quartics, logarithms, trig functions, exponentials, everything under the sun. Every way to go through the origin would have to be considered if that's the way we're going to approach proving that this limit is equal to 0. All those curves have to give the same result, and we just can't test every single one of them. There's just too many functions out there. Even if we could get some general categories like we did with the lines on the previous example. So one way we could do this is to go back to the definition. Recall our definition for the limit. Here we'd have to use our epsilons and deltas and do stuff with them. That is a fairly complicated method, and most people are going to struggle with that. I definitely admit that most people don't really understand the epsilon and deltas quite as well as we'd like them to. It is a fairly complicated thing to get used to. I even struggled with that back when I first learned calculus. So if you do want to look at a way of doing that, you can look at example 4 on page 947. They actually take a similar type of function, another rational function in fact, and they prove that it has a limit of 0 at the origin. I mean, we could do these things at different points, but we're kind of sticking to a theme here, I guess. I'm not going to do that here. What I'm going to do is show you a different way to approaching this. We're going to make use of the fact that we know that for any x squared is non-negative. This is at least 0. And so that means that x squared plus y squared is always at least y squared. We're always adding a positive number to y squared. And so we're always, well, just say non-negative number. We're adding either a positive or 0 to y squared, and so we're going to get something that's at least as big as y squared. If we take the square root, then what that means is that the square root of x squared plus y squared is always bigger than or equal to the absolute value of y, because that's what the square root of y squared is. But that's what that's going to turn into. Actually, I should put the y in the middle. That y is always between negative square root of x squared plus y squared and positive square root of x squared plus y squared. If we take this one more step, we can go ahead and divide everything by y squared, because we're assuming here that we're not dealing with the point 0, 0 right at the moment. So that means that y divided by the square root of x squared plus y squared is always between negative 1 and 1, regardless of what x and y are, as long as they're not both 0, so we can actually write this down in the first place. Now this is looking very similar to the function that we want. The only thing that's missing here is the x. So let's go ahead and multiply everything by x. Multiply everything by x. Well, this is actually not true, technically. This is only going to be true as long as we have a positive x. Because if we have a negative x, it would switch the inequality signs. We end up going the other way. So what we're actually going to do is introduce absolute values here. That xy over the square root of x squared plus y squared is always between negative the absolute value of x and the absolute value of x. But what does this mean? This means that our function, our f of x, is always between these two simpler functions. And we could look at the limits of those simpler functions and get an idea of what happens to f. Now, it really shouldn't be too hard to see that if we take the limit as xy goes to 0, 0 of absolute value of x, that we do get 0. In fact, the y here is almost not important, though technically we are trying to work with functions to variables, so we'll go ahead and keep it there. In fact, putting a minus sign here doesn't change much. It would just make it a negative 0, but that's still 0. So let's actually just say plus or minus square root of x equals 0. Here, plus or minus the absolute value of x is going to 0. That's what I want to say. So what's that saying? Well, that's saying that this side is going to 0, that side is going to 0, and so this thing that has to always be between them, this trap between those two surfaces, is also going to 0. So that, yes, our limit here is 0, and that's a proof. This is actually called the Squeeze Theorem. And you may remember it from Calc 1, back when you're talking about limits in Calc 1. It's just saying that if a particular function is between two functions that are going to the same limit, then the function that's trapped in between them is also going to that limit. And so we do get the answer that we were looking for. We can even plot what those look like. So I think, can I just put in this? No, that just tries to graph it as a function of one variable. So let's say f of xy is equal to the absolute value of x. Will that plot it right? And actually, let's color this a little bit differently so it stands out a little bit better. Let's do that color. So here you can see that the red surface is always below our cyan surface. If we were to plot the other one, say g of xy is equal to the negative absolute value of x. And again, we want to have a different color. Maybe we'll make this one a green. Our red surface is always above the green surface. And so our red surface is always between these two surfaces, and so there's only one place our function could go. It's squeezed in the middle there, and so it has to go to 0. It's just absolutely required. So that's one way we can approach finding these limits, if we don't have continuity at least. Now, we could actually do everything we said with the functions of two variables can be extended to functions of more variables. But let's actually simplify our notation a little bit. So we can always associate the point x1 through xn. So this is a point in n-dimensional space. If you don't want to think about that, you could think about xyz, though instead of x, y, and z, we'll do x1, x2, x3. We're going to associate this with a vector. The vector x, we put this as boldface if this was in text, but it's the vector with components x1 through xn. Or here, x is the vector with components x1, x2, x3. Once we make this association, in fact, this going back and forth here, we're going to associate the function of n variables with a function of the vector. So here, it looks like we're putting one variable in here, but we're putting a vector into it. So we're putting in different components into this function. And we're associating that with just the function of n different numbers. That'll make it a little easier to work with. And we can talk about a vector x going to a vector a, meaning the same thing as the point x1 through xn going to the point a1 to an. We're going to treat those as the same kind of thing. And once we make those associations, basically trying to use vectors here to make sure we don't have to do too much writing, we can get a definition for what our limit means. So we're once again going back to the epsilon delta stuff, but we're saying that the limit as a vector goes, the vector x goes to the vector a of the function of the vector x equals L, means that if we still have to be in our domain, all that kind of stuff, but if the distance between the magnitude of the difference between x and a, this is just saying the distance between the point x1 through xn and the point a1 through an, if that distance is less than delta, then the value of the function has to be within epsilon of L. Basically, as long as the vector x is close to the vector a, then the value of f of x is close to the value of L. We can also define being continuous at x equals a as meaning that the limit as x goes to a of f of x equals f of a, which looks exactly as our definition was back in Calc 1 for continuity of one variable functions. Except here, the x and the a they would be bold if we put them in text. So these are representing vectors. But really what we're saying here is our definitions are just the same as our definitions as they were for one variable, even though we're running into some more issues about proving our limits exist because we have all this stuff about more directions to approach a. But really, I don't want to do any more examples of this. They're all basically just going to be higher dimensional versions of the examples that we just did, and we wouldn't be able to draw any pictures for them, at least not without level curves, or level surfaces, really. So I'm going to go ahead and leave it there. Just be aware that most of this is kind of the cases where things break. We're talking mostly about where things are more broken rather than when they work. Most functions at most points in their domain are just going to work just fine. So don't stress out too much about these. Just be aware that we have to be very careful when we look at some points on surfaces, because they may not work the way you might expect them to. So I'm gonna go leave that there. We do have a homework assignment for this section and the last 3 sections that will be due next Wednesday. but this one and the last two were rather short. It's the one before that's the lengthy one. So I'll see you guys next week.